Welcome everybody to Sustainable River Basin Management, Module 2, Part 2. Today we will be speaking about water resource availability. Let's look back at our water cycle. When we look at the global water cycle, we can apply this very simplified equation and estimate water resources at a global scale. When we come to river basin, and especially to watersheds and sub-catchments, then it becomes more differentiated. Then we have to account for temporary deficits and for temporary surpluses for our water resource availability assessments. Let's look at one of the ways of analyzing these temporary water deficits and surpluses and their applications. We can derive from climate data a seasonal water budget in a quite efficient way. I've chosen an example from a report produced by the National Hydrology Institute in Ruki, just for you to be more familiar with the climate data. And we have here a typical water deficit, water surplus analysis graph, which shows us here one hydrological year, and it shows us here millimeters, and both evaporation and precipitation data are plotted into one graph. What we can see is, in this particular case, the typical Indian monsoon, one monsoon in this case only occurring here. We have our precipitation data following this line, very steep, and our evaporation line following here. And we can see two very remarkable points which are very important for water availability analysis. One, the point where our precipitation starts to exceed our evaporation, and this is where soil moisture recharge is taking place. It begins to take place. It essentially means that we replace our soil moisture storage, and when we reach this top point in our graphical visualization, we reach the point where the soil moisture compartment is being refilled and water surplus is occurring. And this water surplus means that we're starting to recharge our groundwater compartment, and we may observe floods in our region. And then our precipitation will continuously decrease, whereas our evaporation continues, and at this point becomes dominant. And this is where our vegetation, from this point onwards, our vegetation will start use and survive on our soil moisture contents up to the point where the soil moisture will be used up completely by our plant activity and by our evaporation processes, and at that point we speak of a water deficit. Coming back to our starting point, the maximum water deficit is also our so-called wilting point. This is when plant life will not be possible anymore because plants can't access the remaining amount of soil moisture in our soil moisture soil compartment. In that case, we speak of a water deficit. Now, coming to the term renewable water resources, the availability of water resources is essentially linked to the renewable amount of water. And what we mean by renewable water is the resources measured and available over a long-term average flow, surface flow, or in groundwater. And on the other hand, we also distinguish between non-renewable water resources, and those are water resources occurring in deep aquifers. Deep aquifers are deep-sitting groundwater-bearing formations where recharge takes place along geological timescales. We also call this fossil water. And by introducing the term renewable water resources, we are essentially moving into a water resources concept away from simple hydrological cycles or hydrological budgets. Now, let's ask the question, what do we mean renewable and at the same time sustainable? Remember the systems components that we have talked about earlier of the stock, the flow, feedback loops, and communication. Now, renewable systems are essentially controlled by flow, means the recharge rate, recycling rate, etc. And when renewable systems collapse or go extinct, when the supplies are overdrawn, or when the resilience or coping capacity has been overstretched. You can think of any biological matter, and in those cases it's more obvious, but the same applies to our water resource system. And for non-renewable systems, those are controlled by the size of the reservoir or the size of the storage that we have available, and by using those storages, those reservoirs, they get depleted or eventually completely used up. Those are, if we break it down, also renewable, however, over geological periods of time. Just keep in mind, biological species have generally a lifetime of about 500,000 years. Now, if we want to know and conduct water resource availability assessments, we are working with, we have to work out our actual resources, and the actual water resources are the sum of the external and the internal renewable water resources, whereby we mean by external renewable resources the amount of water that has to be will be reduced or taken out by an upstream user, an upstream country, for instance, or the amounts of water that may be added to our internal flows due to interbasin transfers. And on the other hand, our internal renewable resources are those natural renewable water resources which are generated by rainfall inside a specific territory, example, a country. Now, important is when we come up with actual water resources amounts, that those vary very much over years, over seasons, and for that reason we have to build in those interannual variations. This in terms of consumption and in terms of water quality patterns. Just think of agriculture taking place within a catchment area. In some areas there may be seasonal climate variations where certain areas will be under a crop production that requires irrigation, and at some times there will be, after the harvesting season, a lay season where no irrigation is taking place and thus less water is required. The same applies to water quality. Now, in addition to these actual resources, we then have to differentiate still the so-called exploitable, or nowadays more used the term sustainable water resources. And in those we have to account for the socioeconomic and environmental bounding conditions of a region. Now let's look at one global example which shows us our total actual renewable water resources in 2008. And what we see here in the scale is from purple no data, an orange lower amounts of total actual renewable water resources to a dark blue, fairly high total actual renewable water resources. Now, what we can see here is that actually India is one of the water-rich countries if we only account for the total actual renewable water resources. It's one of the upper 10 so-called water-rich countries. So keep in mind that those renewable water resources are computed on the basis of the water cycle. I can't emphasize this more strongly enough. This is the basis based on our water cycle. Now, this picture changes very much when we look at the renewable water resources per capita. And we have here the statistics provided from this UN database, which I suggest you to check out yourself and also make use of this for your own studies. What you can see here is that the scale is from a light blue to a dark blue. Light blue, very low, fairly low amount of renewable freshwater resource per capita, and dark blue, fairly high. And we see that India is very much on the lower end in this case. How is this possible? A few rough explanations could be due to the very specific climatic conditions or monsoon. Some of the parts of the country receiving only one monsoon, some others 2 monsoon periods, and water storage, and linked to the water storage, water quality. So if we have a very short but intense rainfall season, not all of the water can essentially be stored and remain available for later use in the country. So what this also implies that a lot needs to be done on groundwater recharge. Remember that groundwater contributes to our runoff. It maintains river flows and to surface storages. Now, we can ask ourselves if we have what we have in terms of water, renewable water, freshwater resources, what else if this water is not available? Where can we find additional water? Is there a way to find additional water? One solution could be interbasin transfers. We may get water from transfer water through pipes or canals from another water-rich, water surplus region to use it in our basin. But looking at the water cycle, there might be also some additional sources. And we may have heard about these concepts, the green water, the gray water, the virtual water. You may have heard about non-conventional water, and also about bottled water, water mining, water trade. So what about those things? Is this really an additional freshwater source that we could build on? Let's look at blue, green, and the gray water concepts. What do you mean by blue water? It's essentially all the surface and groundwater runoff. We have seen this in our water balance discussion. So, and where we can save water is on water supply, on the way we conduct our water abstraction, to manage our water losses from piped systems and from other water distribution systems. And we may manage our evaporation losses from water bodies and storages. This is how we can measure and also influence our blue water. So this is a real field where we can do something. We can measure it volumetrically, and it is part of the water cycle and influenced simply by water abstraction and distribution. Now, looking at the green water component, what is meant by green water is the amount of rainwater that is converted into soil water for plant uptake, or for water that is directly used and evaporated from the vegetation. So you see that this is not water that we can visibly catch or see. It is water that is bound in the soil and water that is taken built into vegetation, into plant material. So essentially we are talking about the water in non-irrigated agriculture and in pasture from a human perspective, and in grasslands and forests from a general ecological perspective. Now, this is translated into actual evapotranspiration, and it's part of our natural water cycle, and we can measure this, although it's not a routine measurement. However, it simply indicates irrigation needs and also is a measure of irrigation efficiency, and it simply helps to plan crop cycles or the selection of appropriate crop species for a region. So we can influence that green water component as well, but not in the way of obtaining fresh water for us for drinking water purposes. It's simply helping us to improve in agriculture. Let's look at the grey water component lastly. This is essentially a polluted water. What is meant from this? It's polluted water from domestic use, and we account for that in the form of the amount of water required to dilute polluted water to a permissible level for discharge in freshwater systems. So what we mean by permissible is it's a very stretchable, flexible term here. It depends on legislation, if there's any legislation in place, how it's been implemented. We will come back to this at a later stage, but what we see is that it's a measure of qualitative properties of water. So we are not increasing the availability as such, we are just differentiating between qualitative properties. And it can be coined into a financial figure, into consumptive losses and into opportunity costs. We will come back to these concepts at a later stage. They are very important. Now, what you may have heard about also is, and what the question is, could be an additional water source, is virtual water. And what we mean by virtual water is the entire volume of fresh water that is required for a service or a good throughout the entire value chain. This means from production to processing, harvesting, processing, manufacturing, transportation, consumption, and waste dispersal or reuse. This entire chain, we are using water openly or less obvious. And this can be accounted for, and the concept for that is also called water footprint, but this is essentially an economic concept. So it gives us economic figures which help us to improve our efficiency and conduct a sustainability analysis, and we can use this for strategic planning. So this is not as such giving us an additional amount of water that we will have instantly, immediately available. Now, this footprint, just summarized in a few examples, what this means is visualized here. This is a figure from the Stockholm International Water Institute. You can check out more literature on their site. And what you can see, if you compare this with other sources, you will see that those figures will vary quite a bit. And what you can also see is that it's not very easy to compare one item with the other. So in some cases we speak here of liters that are used per number of or one individual animal. The other time we speak of liters of wine to produce, and the other time it's an individual bread or something else. So the units vary very much, and we are not really able to compare one thing against another one. But this gives us an idea of some of the amounts, but those large numbers can really not tell us that this is problem compared to something else where the number here is appearing small. So keep this in mind when you read such information. Now, what the virtual water flow concept can be applied in a different way, which can be quite useful, and I want to demonstrate it to you here. When we apply this to a transfer of water from one country to another, this is again virtual water, so water embodied in products. And because most of our water is, our virtual water is incorporated in crops, 70% globally, 20% in livestock, and the rest in industrial goods, we will be looking at a figure showing us the regional virtual water balance by region for crop trade, for agricultural product trade. And what we can see here is a scale from a positive blue, dark blue, to a highly negative, dark red, whereas the blue positive means an export from this region to another region, whereas the red means an import of virtual water into that specific region. And we see that the world essentially is divided into large regions which export water, means virtual water where a lot of production, of agricultural production takes place, and where this virtual water is being removed from this region and exported and used in some other regions, and some regions import a lot of water in addition to their internal renewable available water. Now, what is this useful for? Essentially, it can help to develop a regional, national water policy. Basically, as you want to put your available water resources into an agricultural product, or you want to invest in other uses which maybe need less of your country's available water resources. Now, let's look at the non-conventional freshwater that I had listed before and look into this global water cycle again. What we mean by non-conventional freshwater is the water that comes out of desalination of salt water. We are essentially tapping our oceans for that purpose, and the reuse of urban and industrial wastewaters. This could be treated or not treated, and it includes agricultural drainage water wherever it's been collected. Now, thinking of this, we have been looking at our water balance or water budget always from a freshwater perspective. We have not really factored into our water budgets or local water balances saline or ocean water component. And there are reasons for that. So this non-conventional freshwater is considered to be simply a complementary supply source. So it's a source in an emergency. It's a source of water that can ease an extreme situation, but it should not be considered as a long-term freshwater source, supply source. It has become very important in some regions which are affected by extreme scarcity of renewable water resources. This non-conventional freshwater has to be accounted for separately from our natural renewable water resource balance, from our freshwater cycle, although it eventually will be feeding back into our freshwater cycle in the form of wastewater. It will generate runoff and it will potentially recharge our groundwater. And finally, let's reflect upon bottled water, and I'm putting next to this term bottled water the privatized water. So bottled water means that it's water put into a container and sold as such, as a good through private enterprises, private operators. So we remove our water from our water cycle by putting it by packaging it. It becomes it becomes an economic good. Now, what this means in a globalized world is that we can take water from anywhere, any point on our globe, and package it here, transport it, and sell it somewhere else where people will consume it. And this has been reflected in this map here, which shows us our water bottling exporters or exporting countries. And there are very few countries dominating this export market of bottled water, although some of the data may not be complete. And then we obviously will have importing countries where these bottled water containers will be sold again. And again, there are only a few countries which consume those bottles. And what you can see is that some of the large exporters here are not essentially the importers of it. Some even import other water from other regions. So it shows us that water availability will be reduced in those. We are transferring water from one part of the world to another part through the bottling mechanism and privatized mechanism of it. So it disturbs our freshwater budgeting, but it also disturbs our water rights base in many cases and our water accounting in general. So this is very critical and something that is very much on the rise and needs a lot of attention. Once we have those importing and exporting mechanisms in place at a global scale, then we can see a number, just a very few, low number of bottling companies which dominate this market, this business. And what you can see is that essentially, again, our world has been divided into some domains where these large corporates operate very much independent of any water catchment, any water balances, or any freshwater availability or country water necessities or priorities. So this is very critical, and we should keep this in mind when we talk about sustainable water management in the next run. Thank you for your attention, and I see you next time again.